Hello, a great welcome to this presentation. Today I am going to demonstrate the steady-state vibration analysis through a simple tutorial using SAP2000. So as usual, let me first provide you a brief introduction on steady-state vibration analysis. The steady-state vibration analysis is essentially a frequency domain analysis performed on a structure subjected to a frequency-dependent harmonic excitation. At each frequency, the loading varies with time as a sine and cosine functions. The response is evaluated for a range of frequencies of interest. So a steady-state vibration analysis essentially provides dynamic response of a structure at one or more frequencies to loading of the form P omega is equal to summation of Sj Fj omega into Pj into cos of theta j plus I sine of theta j over the variable j. So as you can see that the loading consists of a series of functions that are characterized through a frequency function Fj omega as well as a phase angle theta j. So let me provide you a brief description of the various parameters here. Fj omega is a frequency function directly defined through a steady-state function in SAP2000. Sj is a scale factor, theta j is a phase angle at which the load Pj is applied, Pj is the load represented through load patterns in SAP2000. So let us start with the problem statement. So the objective here is to demonstrate the steady-state vibration analysis of a cantilever beam subjected to a frequency-dependent excitation using SAP2000. We know that SAP2000 is a structural engineering software developed by CSI. So the input data is presented here. As you can see that here is a cantilever beam of a span L, and that supports a machine at its free end. The machine is subjected to a frequency-dependent unbalanced force excitation. So the important parameters are as follows. The span L of the cantilever is taken as 3 meters, and the profile of the cantilever beam is a Euro section that is taken as HE240A. For the problem, we considered a uniformly distributed dead load over 10 km per meter throughout the span of the cantilever. The total static weight of the machine is taken as 30 kN, with the operating speed is taken as 50 Hz, that is equivalent to 3000 RPM. Now for the computation of the unbalanced force, which is essentially the excitation frequency dependent, we have assumed the following parameters. That is, the rotor weight is taken as 0.5 kN, and rotor mass Mr is taken as 0.05 tons, and the rotor eccentricity E is taken as 0.2 mm. These 3 parameters are required for the evaluation of the unbalanced force that is generated by this machine at various frequencies. Okay, so for any steady-state vibration analysis, the first step would be the characterization of the frequency-dependent load, which means that we must be able to describe in detail the definition of the load in relation to the operating frequency omega as well as the phase angle phi. So for the given problem, it is assumed that the rotor is oriented along the y-axis in SAP2000 model. So look here, so this is the x-axis in the SAP2000, this is the z-axis, and my rotor is oriented along the y-axis, and the unbalanced force generated by the rotor is generated in the xz plane. And from our basic understanding of the evaluation of the unbalanced force coming out of the so-called the balancing problem is F0 is equal to mr into E omega square, as is already provided over here. It acts in a radial direction because it's a centrifugal force, and obviously for any phase angle phi, this force F of mr E omega square has 2 components in the x and z direction, which is defined as fx equal to mr into e omega square into cos phi, and fz is equal to mr into e omega square into sin phi. This means that for any phase angle phi, the frequency dependent exciting force can be fully defined as P omega is equal to mr into e omega square into cos of phi plus I sin phi. Thus we find that our load definition, frequency dependent exciting force definition, involves the important terms. The first one is the frequency omega as well as the phase angle phi. Now the scale factor S to apply in the steady state load case is the product of mr into e, and that is evaluated based on the input parameters as 0.00001, and the function f omega is to be defined as a steady state function in SAP2000, and for our present case we know that f omega is nothing but the term omega square. And here is presented a plot of f omega, and this plot is made up to a frequency of 50 Hz, which is nothing but the operating frequency of the machine. And as expected, obviously the variation is parabolic, and we find that along the x-axis we have got the omega, that is in Hertz, and along the y-axis is the f omega defined as omega square. So that is all about the complete definition of the frequency dependent load. In step 2, we shall go for the distribution of the SAP2000 analysis model. So let me directly take you to the SAP2000 in order to explain the various parameters associated with this analysis problem. Okay, you can see that this is the simple model for this cantilever beam that is made in SAP2000. So let me take you through the various parameters used for this steady state analysis. So as usual, let me show you the material property. So here you will find that we have defined a property called steel. So all the properties are set over here. As you can see that the unit weight is set as 0, and the modulus of elasticity E is set as a 2E8 kilonewton per meter square. Now coming to the frame sections, you will find that we have defined a European section HE240A. If you just click over here, you will get all the material properties over here. So you will find here all the dimensions are relevant to the HE240A section, and you will also be able to get a summary of all the properties, including, for example, the cross-section area, the torsion constant, the shear area, moment of inertia, etc. over here. Now let me take you through the various load patterns that is used for this analysis. So here, as you can see, that we have defined a total of 4 load patterns, and as far as the dead is concerned, that will cover all the loads that is applied as uniformly distributed over the beam, and the machine means it is a self-weight of the machine that is applied at the free end, and this ECCX and ECCZ are the unit loads applied in the X and Z directions. So let me just show you the loads for more clarity. So you can just go over here, display, and here in the dead load, so you'll find that we have applied a total superimposed load of a 10 kilonewton per meter all along the length of the cantilever. Now let me take you through the machine load pattern. Here you will find that we have applied a concentrated load, that is a self-weight to the machine, that is 30 kilonewton at the free end of the cantilever. Then we have applied a unit load under ECCX. Under ECCX we have applied a unit load in the X direction. As you can see that here we have applied a unit load. Now similarly in the other load pattern, that is ECCZ, we applied a unit load in the Z direction, plus Z direction. So these are all the loads, details of all the loads that is applied in the various load patterns. Now let me take you through the definition of the steady state function, which is a part of defining how the load, how a frequency dependent load is applied over here. So we'll go over here, define. So here you'll find that there is one called functions. Under functions, you'll find there are different function types: response spectrum, time history, etc. And the last you'll find there is a steady state one. So here you'll find we have defined a function called f squared, which is nothing but it's an omega square. So if you want to see the functions, so so we'll select this one, f squared. So this is a function. So here, as you can see, that we have imported a text file that contains the various coordinates associated with omega and f of omega square. And as is very clear, the relationship is parabolic. And be very careful that here the frequency units are to be properly set, and here the frequency unit is set as hertz. So for example, if you move the cursor all along the graph, you'll get all the coordinates, that is the corresponding omega value as well as omega square value over here. So this is the definition of the steady state, which will be used later on in the definition of the steady state load case. Now let me take you to the various load cases. So here we have a total of 4 load cases. So let me just show you the details of this load cases. For example, dead. So as you can see, that as expected, the load case will be set as the static, and it will be the analysis type will be linear. And here we have used a load pattern of dead with a scale factor of 1. And now going to the model, obviously we know that is a model analysis load pattern, load case, and here the load case type will be the model, and we are using the eigenvectors, and we have selected the maximum number of modes to be considered for the analysis 6, and these are the other parameters that is used for the analysis. Now coming to the other third one, the load case, that's a machine. You'll find that here again it is the load case type is set as a static, analysis type is linear, but here the only difference is that the corresponding load pattern that is used is machine with a scale factor of 1. Now let us discuss a little bit more detail into the load case name, that's a steady state load case. So if you want to see the details, you'll find that this load case name is set as a steady state, and here the load case type is taken as a steady state, and the solution type is taken as a direct, and the stiffness to use is the 0 initial conditions. And if you look into this load case, you'll find that 2 load patterns are simultaneously considered in this load case. One load pattern known as ECCX and the other load pattern known as ECCZ. And here is the location where you need to enter the steady state function. In both the load patterns, we find that the steady state function is the same. And here the scale factor S need to be entered, which is same as 1 into 10 raised to minus 5 in both cases. And remember that for the load applied, for the load pattern applied in the x direction, the phase angle has to be set as 0, whereas for the load pattern in the z direction, it has to be set as 90. And in both cases, the angles will be set as 0. And now if you look onto the frequency step data, that means that this provide us what are the frequencies to be considered in the response plots or in the response analysis. As you can see that here the first frequency we have set as 0, and the last frequency as 50, and the number of increments as 50. It means that we have requested frequencies 0, 1, 2 up to say 50 hertz. So there will be altogether a total of 51 values. Now if you look into the frequency step data, you'll find that there is a column known as a set addition frequencies, and this is also interesting because we find that in the response steady state response analysis, there is a sudden pickup of the responses near the model frequencies. Accordingly, what we need to do is that we need to specify into the program some important options, like for example add the model frequencies and also add deviations from the model frequencies. This is to ensure that all the minor changes in the model frequencies are captured in the response analysis. For example, if you look over here, you'll find that we have set up some fractions like, for example, minus 0.05, minus 0.02, minus 0.01. Similarly, on the positive side, 0.01, 0.02, and 0.05. So this is regarding the frequency step data and the associated frequency parameters. That is also very important for us. And now finally coming to the damping, we have set the high static damping, and if you just show over this, you'll find that we have set up a stiffness proportional coefficient of 0.04, which corresponds to approximately viscous damping of 0.04 by 2, that's equal to 0.02. So this means that we have defined all the load cases that is pertinent to this problem. And now I would like to show you the last one, that is the so-called the mass source, because we are running an eigenvalue analysis, which means that we need to define explicitly or clearly the mass sources. As you can see that the mass sources are set to be computed from the load patterns. We have used the load patterns, dead end the machines, each with a factor of 1 for the computation of the mass to be used for the eigenvalue analysis. So that's all regarding the parameters that is used. So once you run the analysis, you will get the various properties or the various analysis results. And basically the analysis results that comes out of a steady state analysis, it comes under two categories. One is the model analysis, and the second one is the response plots we obtained from the steady state analysis. So for example, if you just want to see the model results, you can just go over here, display, and you can ask the program to show the tables. So for example, here I have set all these results. So this provides you all the details regarding the model participating mass ratios. So here you will find that we have considered a total number of 6 modes, and that adequately captures a period of up to 0.005, which is equivalent to 200 Hertz. That is good for our analysis because the operating speed is 50 Hertz. And as you can see from here that we have mobilized almost a participating mass of say 98.4 as far as the response in the z direction is concerned, and a similar mass participation is mobilized in the case of the rotation about the y-axis. That is, if you look over here some ry, you will find that we have mobilized around say 99.9%. So that is good for our analysis, and it's also possible for you to plot the various move shapes. So you can just go over here and you can select, for example, model. Suppose I am interested in a say fourth mode. So I can just press the fourth mode, and okay, so you'll find that this is the mode shapes for the fourth. In a similar way, we can also get the corresponding mode shapes. And finally, as far as the steady state analysis is concerned, we need to also obtain the corresponding response plots. So you can go over here. So I'll just keep it as okay, and straight away go over here, display. And here there is something like a show plot functions. For example, here I have defined the joint 2 to represent the response plot corresponding to the amplitude in the z direction. So if you want to see what this plot function is, you can just double click here, joint 2, modify it. You'll find that it is nothing but it is a plot function relevant to the joint ID 2, wherein the vector type selected is displacement and the component considered is UZ. So if you want to plot this function, you can just select this vertical function as a joint 2 here and display. So this is the response plot for UZ, and as you can see that there is a sudden jump of the response quantities very near to the model frequencies in the z direction. But as the machine approaches the operating speed of 50 Hertz, you will find that the amplitudes are well within the specified limits. So that's all regarding the various parameters that is set for this simple model. But as it is a steady state analysis, we have got a lot many parameters to be set, and we have to be very careful over here because we are obtaining the response of the structure over a specified range of frequencies. So now let me go back to the presentation and provide you a little bit more detail regarding the various analysis results. Okay, fine. So now let's proceed for the results from the SAP2000 analysis. Obviously, for a steady state analysis, the result essentially consists of two sets of parameters, one related to the model analysis, and the second one is the response quantities obtained from the steady state analysis. So first we will take up with the model analysis results, a summary of the model analysis results, which essentially consists of the mode number, the associated natural frequencies in Hertz, as well as the time period, and also the total mass participation in the various deformation modes are provided over here. So as you can see that the first 6 modes are good enough for us, because as you can see that the 6th mode has got a natural frequency of 200 Hertz, which means that our operating frequency of 50 Hertz is obviously covered well within the number of modes that is covered in the analysis. And looking into the analysis results, we find that for the response in the Z direction, the 6th mode is good enough to achieve a model participation of 98.4%, and with an associated rotation about the y-axis of 99.9%. So the following conclusions are arrived at. First 6 modes, as already explained, cover frequencies up to 200 Hz and therefore include an operating frequency of 50 Hz. For what concerns UZ and RY, and because we are going to obtain the response plots in terms of UZ and RY as a part of the steady state analysis, we find that the total mass participation is close to 1.0. Therefore, we conclude that the model analysis results are good enough in order to provide a good reliable results in terms of the response quantities obtained via the steady state analysis. Now here I have also presented some plots of the mode shapes, and this is mode 1 and this is mode 2, and mode 3 is essentially is an axial deformation, so I have not included over here, and this is mode 4 and this is mode 5, and finally this is mode 6. So this is all our detailed review of the model analysis results. So now let us quickly go to the steady state analysis results. So as far as the steady state analysis result is concerned, it provides us the variation of the various response. For example, this response could be the velocity, acceleration, or the displacements or the rotation of at any point of the model, and these variations will be plotted over a range of useful frequencies. So here what is done is, first we have plotted or we have evaluated the response of the free end of the cantilever, that is for the joint 2, in the UZ, that is in the Z direction. So this is a plot, and as you can see that along the x-axis we have got the frequency in Hertz, and along the y-axis is plotted the amplitude of the joint 2, and the unit is microns, that is the 10 raised to minus 6 meters. And this plot is very interesting, as you can see that as the machine starts from 0 and it reaches an operating free speed of 50 Hz, you'll find that some of the critical frequencies are excited. For example, the first natural frequency of the structure in the Z direction is 3.33 Hz, and accordingly we find a sudden spurt in the amplitude of the order of 65 microns, and then as the frequency increases, it reduces down, and again we find that at mode 2, where we have got some contribution of the Z deformation, again there's a small spike in the amplitude in the Z direction, and this corresponds to a frequency of 30.4, and we find that finally at the operating frequency 50 Hz, the amplitude is contained within a very small value of around say 3 or 4 microns. So this is all regarding the response we evaluated for the free end of the cantilever in the Z direction. In a similar way, we have also plotted the response as the rotation of the free end of the cantilever. So here again the same plot, as you can see that along the x-axis we have got the frequency in Hertz, and along the y-axis is provided the rotation of the joint 2 in micro radians, that is 10 raised to minus 6 radians. And just similar to the response of the joint 2 in the Z direction, we also have a similar plot over here, and in this case again we find that the rotation of the joint 2, we find that there is a maximization, or we find that there is a shoot up of the rotation at the specific frequencies identified as the natural frequencies in the first mode as well as in the second mode, that is f1 equal to 3.33 Hz. We find that there is a sudden shoot up of the rotation of the joint 2, and in a similar way at frequency f2, that is 30.4 Hz, again we have got the rotation of the joint 2 getting shoot up to a maximum value of 40 micro radians, and we find that at the operating frequency of 50 Hz, the displacement parameters are well within the control, and it is as small as around say 4 micro radians. So I think that that's all regarding the detailed evaluation of the results from SAP2000 in terms of the model analysis as well as the steady state response plots. So as usual, please go ahead and subscribe to the channel, and if you have any queries, regarding to this tutorial, please let me know. And if you require any kind of an explanation to any parameters provided through the steady state analysis, please let me know. So thank you and have a nice day.